My name is Akif. I'm going to talk about Volksat algorithm, which is a local search algorithm to solve Boolean satisfiability problems. This problem comes up in many places, and while working at NVIDIA, we came up with some use cases and explored this, and I will try to share my exploration and the things that I've learned about this Volksat algorithm. So let's start with the definition of Boolean satisfiability. Boolean satisfiability is a problem of assigning binary values to logic equations. So I'm sure all of you are familiar with logical equations where we express some logic in a formula with and, or, if, XOR, and many other operands. And this has many applications in the in the industry that helps solving real life problems. That's why it's a widely studied area, and lately with the increased computation power, it is studied even more. It's a NP-complete problem, so the search space and the amount of combinations are exponential, so it is extremely computationally expensive to find solutions to Boolean satisfiability problems. That makes it suitable for heuristic-based approaches like WalkSAT that I'm talking right now, and also there are a lot of other non-heuristic based, non-local search based algorithms. I will mention some of them. Commonly used representations are to represent this problem in Boolean expressions is CNF and DNF. CNF is an abbreviation for conjunctive normal form, and DNF is a abbreviation for disjunctive normal form. I will explain how they look like and how we represent Boolean equations in those forms in the next slide. There are different type of algorithms, but we can categorize them in two different categories. One is complete algorithms that are proof-based and that exhaust the search space if you run them long enough. So for sure, if there is a solution to this, to a set problem, they will find it. Okay, maybe for some problems, maybe it will take years, but the nature of algorithm will eliminate all other possibilities and do the resolutions and find the problem. That's why it's called complete. And the advantage of complete algorithms is that they give you, if it's satisfiable, they can give you how the Boolean equation is satisfiable and give you the satisfying binary values. If it's not satisfiable, if it will give you a proof why this particular equation is not satisfiable by giving you the conflicting clauses and conflicting expressions. So it is most of the time this one is used in the industry because industry needs a complete algorithm and proof of unsatisfiability so that they can change what was wrong in the initial equation. So they can change their design or problem to make it satisfiable. Another approach is the local search or random walk based approaches. So initially it was initial studies on that were stochastical random walk solvers, basically just flipping bits, doing random walks and seeing if the solution is improving. But with the recent research, and by recent I mean maybe it's been 20 or 30 years, but with the recent research, there are additional heuristics that make this random walk process, this stochastic process, converge better. And the advantage of these local search based solvers is that they converge fairly fast, so they are not looking for proof of incompleteness, or they are not resolving every particular clause that are in the equation, but what they are doing is they are trying to converge as fast as possible, and they are usually good on medium to easy problems. I will come to the analysis at the end. So a Boolean equation looks like this. So we have literals or atoms that can have true or false value. And so literal and atom is the same name. So they are used different as the same meaning in the literature. A clause is an equation that is consisting of the literals and that is connected with and or operators. So the thing is, we have also a negation operators, which is the not here, and that is also part of a literal. We can also have a clause and a literal at the same time. So at the bottom, A is just a clause and also a literal. Here up there in the third row, A or B is just a clause. The second row, we are seeing a conjunction of clause and a literal. So the CNF and DNF are a convenient way of representing these Boolean equations so that they are consistently represented, and also it's easier to solve them with the solvers. CNF is a conjunctive normal form, so it's a conjunction of clauses, and each clause in a CNF is a disjunction of literals. So the key point here is a clause cannot have a not operator in the middle, in front of it. So the not negation iterator, negation operators should be in front of literals and not clauses. That's the important aspect of this kind of representations. And at the end, we will have this disjunctions in many groups of disjunctions that are connected with conjunctions together, and that will be passed into the SAT solver that is optimized and that knows how to solve this kind of expression, this kind of structure. DNF is disjunction of clauses, so it's the same concept, but instead of having conjunctions between clauses, we have disjunctions. And the point here, so what makes it easier here is that in the CNF version, you need to make at least one variable, one literal, true within the clauses to make the whole equation satisfiable. In the other one, you need to make at least one clause satisfiable because they are all connected with n. And different solvers might accept different type of equations, different type of types, but the most common one is the CNF, and they are optimized for solving that. So the good thing is that they can be converted to each other with logical equivalences, such as double negation, De Morgan distribution, or all the other. I mean, we know this mathematical properties as well, equivalences that we can use. I will quickly go over one of them. I'm sure most of you know it, but for example, we in the first example, first row, we have a conjunction between f. So we have an or between f and the clause, and we have an and between gn and h, but we want to convert it into a CNF form. What we do is we basically distribute f over g and h, and it becomes CNF, and yeah, you can check the other ones. There are many more ways of creating CNFs and DNFs or converting them. So SAT solvers can, so in real life, you have more constraints than just or, and, not, if, but you have some constraints such as same, which enforces that all the variables for the given, all the given variables should be exactly the same. And one can formulate that with the equation that I show here. So all x1, x2, and x3 should be true, or all x1, x2, and x3 should be false. Or we can have another type of constraint, which is exactly one. So what we want to achieve is we want to have exactly one of x1, x2, and x3 as true. So what we do is we define a phi1, which says x1 or x2 or x3 are true, and x1 and x2 cannot be true at the same time. x1 and x3 cannot be true at the same time, and x2 and x3 cannot be true at the same time. So if you express this like this, then you will have this exactly one constraint in your SAT solver. There are many more, but just to give you an example, for example, at least k or less than k or exactly k amount of them should be the same or should be true. Then here you generate a matrix of variables, so it can't be simply generated with k variables, but you need to create a matrix of variables to represent those kind of equations. If anybody is interested, I can show you the references for doing that, but I will skip that. So some problems that can be solved by SAT solvers are, of course, constraint satisfiability, where you have constraints and an equation of constraints, whether if there is any assignment that satisfies this. Graph coloring algorithms, where there are many forms of it, but the most known form is no adjacent edge can have the same color, and you can express it with simple Boolean logic, but probably there will be, as the graph size grows, it will be very complex, as this is a NP-complete problem that grows exponentially. There are some polynomial time solutions to graph coloring problem when colors are 2, but if it's 3 or more, it is exponential, and you need some advanced or heuristic-based solutions to find the result to that. Scheduling to see if there are, let's say, any conflicts for scheduling let's say a class, teacher, a student, and conflicts of different exams. So this is one example. You can schedule you can schedule machinery in a factory, but these are, as the size grows, these become extremely hard to represent with Boolean equations, because the number of variables and the cardinality of the input and output is growing a lot, and you need to one needs to have many variables and many clauses to represent such complexity. So for scheduling type of problems, usually people use other approaches such as MIP solvers and or heuristic-based scheduling solvers that are specialized for them. Binary neural networks, it's I think, a relatively new area. Maybe you can correct me if it's not. It's basically, instead of having weights and activations as floats or halves, they are binary, and output is also binary. So what we want to find out is if there exists a model, a set of parameters that can accommodate all of our training data. And to do that, we basically fit a SAT solver. So when you write this, when you write a SAT equation, so Boolean equation, to represent the model and the truth values of the input, the SAT solver will give you, if there exists, if it's possible to fit a model for this binary neural network. If not, you can maybe remove some of the inputs so that there will be a model. I mean, why would you might ask, why would people use binary neural networks? Because it's much faster than normal ones. It's like up to 60 times faster. Binary decision trees are more or less the same story. So you just do binary decisions and to see if there exists a decision tree that fits the data. So how do we saw CNF, but how do we actually express problems in CNF and convert them in CNF? Actually, there are many different encoding and conversion strategies. That's a research area itself. So it's completely deep area, and also the problem of P equals MP, like P versus MP comes to here as well. So the problem of P versus NP is there because if you can find that there's a polynomial time solution to any NP complete or hard problem, you will have a polynomial time solution to all the other NP complete problems. The reason for that is NP complete problems can be converted to each other, and I think that is proven. I don't have the proof for that, but you can convert all the NP complete problems to each other. So the point here is to find the best encoding so that first, your problem is fully represented. Second, it fits the SAT solver so that it is not taking too much time and you're not using a lot of variables and clauses, because an encoding strategy might introduce an order of magnitude or a couple of orders of magnitude more clauses or variables, and that will make it basically very slow or impossible to solve. These CNF equations are expressed as a standard format, and this format is called Bmax, and that is basically it's a basic text file where you have a variable ID and clause ID, and the variables that consist of those clauses with negation is represented as minus, and if it's the literal itself, it's without negation. And then this will be the clauses that we will have, and we will try to find the assignments to these clauses. So there's also an issue of encoding and conversion efficiency. So even if you can convert a problem to CNF, like a SAT problem, it might be expensive to actually convert that problem to CNF. Sometimes it takes quadratic time or even more, and you might want to either avoid that or use a more efficient version. And the result also needs to be small so that the SAT solver can solve the problem. So what is an example? So I will give a very small example here that I found interesting online yesterday while I was preparing the presentation. So package upgradability. So when we install a package from, I don't know, some package manager like pip, apt, or whatever, when we want to install a package, it shows you, which dependencies that this package has and which dependencies that this package has conflicts with, so that they will have to be removed. So what is the amount of packages that can reside on a system altogether, given those conflicts and dependencies, is actually a satisfiability problem. And we can represent, So we have like 4 packages, let's say P1, P2, P3, P4, and P1 depends on P2 or P3, and it has a conflict with P4. So P2 has dependency to P3 and no conflicts. P3 has a dependency to P2 and no conflicts. P4 has a dependency of P2 and P3. So how do we express this as a Boolean equation and find find if all packages can reside? If not, why? So as you can see, we can divide them into different categories. One is first is dependency. So in the dependency part, we say that in order for P1 to be installed, we need to have in the system P2 or P3. So if P1 is true, this means that not P1 is 0. So at least P2 or P3 must be true. One of them should be in the system. And the same is similar with P2 and P3. P2 depends on P3 to be on the system, so that this clause is satisfiable, and so on. For the conflicts, we want to make sure, so if you remember for the conflicts, let's say P1 has a conflict with P4. In order for P1 to be installed in the system, P4 should not be installed. So if P1 is 1, which means the result is 0, the P4 should be 0, so that this is satisfiable. And then the packages that can be installed are just P1, P2, P3, P4, and they are themselves clauses. I have written the resulting equation as a single equation but in the bottom. So is there any assignment to P1, P2, and P3 that makes this equation satisfiable? No, there isn't, because of conflicting clauses, and these conflicting clauses are actually given by proof-based SAT solver to you, but with WalkSAT, it will just say false, so you will not be able to satisfy it. The reason is that with the conflict of P3 and P4, these two cannot reside on the same system at the same time, so that either one of them needs to be false, or this doesn't work. So what algorithms are there to solve Boolean satisfiability problems? The most common ones are DPLL. This is the initials of 4 researchers that found the algorithm. DPLL is basically a DFS algorithm that does some unit resolutions. So it's not just brute force DFS on this Boolean search tree, but also along the way, it explores which values, which clauses are redundant, and which unit resolutions have to be done. And a upgrade to this is a CDCL, conflict-driven clause learning, and that is more or less the same as DPLL, but on top of that, there are learn clauses throughout the DFS search. And when we learn these clauses, we add them to the equation so that this prunes the search space, so the DFS search space that we are going to have, and make us converge faster. So I see this as kind of a memoization in dynamic programming, but it's a different form of memoization. Instead of memoizing the values in an explored path, we actually infer what kind of clauses are not, what kind of values, and what kind of values are not possible together, and encode it for the future search path of the DFS. I'm not going to talk about these two today, but yeah, if you guys are interested in a couple of months, maybe I can study a bit and talk about them as well. So the other algorithms include local search algorithms, and I think the most promising one is WalkSAT. And today I'm going to talk about WalkSAT. So it's basically a stochastic walk algorithm, I wouldn't say random walk, because there are some heuristics that help help the solution to converge to a local minima, so that it is not completely random. So what we do is, it's a heuristic approach to explore search space. And if you guys, if any of you were here in my first talk, I know Brock and Berin was here. So it's very similar to the local search steps that are done in routing examples. But here, a step of local search is not basically switching nodes between the graphs, but it's actually flipping a bit, like changing the Boolean value of a variable from true to false or false to true, to see if we are improving. I will come what is improving means. Our aim is, along this stochastic local search, is to minimize the number of unsatisfied clauses. Okay, so this is wrong. So this should be clauses, because assignments are not there yet. We want to find the assignments that minimizes the unsatisfied clauses. I imagine the search space of a Boolean equations as a multidimensional stairway, and that contains a lot of plateaus. Why I say plateaus? Because most of the time you flip a bit, but the number of satisfied and unsatisfied clauses don't change at all. They stay exactly the same. And the stairs, why I say stairs, because it's extremely discrete. So you just jump a couple of satisfied clauses up and down. So it is pretty important to be able to escape the plateaus and also the local minimums, because you might be stuck in some bottom of the staircase, I would say, in a pit. So the algorithm is like this. So what we do is we try many number of times. So you can think of it as infinite loop, but most of the time, if we don't find the solution in a given number of tries, which is most of the time somewhere between 100,000 or 1 million, if we don't find any solution within those iterations, we just restart the algorithm with a different initial state, or I don't know, try another algorithm, but most of the time, yeah, start with another initial state. What we do is we start with a random assignment, and we choose a random unsatisfied clause for this assignment. And what we want to do is in this unsatisfied clause is we will flip a bit. So basically change the Boolean value of a literal in this clause, and see if the other clauses that contains this particular literal have also become satisfied, or some satisfied clauses that were satisfied before became unsatisfied by flipping that bit. Our objective is to minimize the number of unsatisfied clauses after doing this, with this that is resulted after doing this Boolean value change. The name of this concept is called break count. So we want to break minimum number of clauses that were satisfied before. So we want to make this clause satisfied, but also we don't want to mess up with other clauses that are already satisfied. There are there are two aspects of it. One is more of the stochastic process part. So you basically flip a coin, and that's your literal or atom that you wanna change the value of. So it's probabilistic. And the other one is you search for the best literal in that clause to find which literal change will cause the least amount of break value in all other clauses. We do this two different things. I mean, usually this P is 0.5, so it's actually a coin flip, but I will show you some other approaches on how we can adjust this P along the way for better convergence or for different situations. The logic behind this is that we want to converge, so we want to actually find the best atom that minimizes the break count, but also we want to do some sort of random walk because local search algorithms converge very fast to local minima and get stuck there. So we want to avoid that, and we want to increase the diversity. So that's the whole. That's also a very, very common concept in other optimization and local search algorithms. You want to keep the divergence and convergence going together. So you want a diverse enough solution that is also converging. And if the solution after this variable flip is better than the current solution, then we update it. By better, we basically number of satisfied clauses. So at least for this case. If there are any questions at this point, we can stop and then continue.
Yeah, will you explain how we choose the best atom, right?
Yeah. So the best atom, so atom or literal. So how we choose it is we search for each literal in the clause and try to flip a literal in that clause and see if we flip that literal, what happens to all the other clauses in the equation? Do we actually break some of them? So are there any clauses that were satisfied before and that becomes unsatisfied after flipping this particular literal? And then we take the count of them. So count of how many clauses that we have made unsatisfied. So that we have broken, basically. It's a break. Yeah. And then we do this for every literal in the clause, and then find the best literal that causes the least amount of break in all the other clauses, and choose that particular literal to execute. So with this way, before we had, n number of unsatisfied clauses. Now we have n minus hopefully 1 if we don't break more, but n minus 1 plus something or more. Because when you actually, so there's the thing, when you make this clause satisfied, some other clause might also be satisfied, but the heuristic is that break less, so it doesn't count the difference between the satisfied and unsatisfied clauses, but it only counts the number of clauses that we have broken.
I see. So this is like a brute force part, right? You try every other literal. So is there any other like smart ways or things to do it, or you just need to iterate over all the 8 atoms?
So all the atoms in a chosen clause. So we choose a clause first, which usually contains 3, 4, 5. So I mean, when we say brute force, it's actually very, very small. So in those Boolean equations, we have clauses, and each of the clause has somewhere between 3, maximum 10. So there is rarely a Boolean equation that have a clause that has more than 10 literals. Okay. And what you do here in the else part to find the best atom is basically look each of those 10 literals and see if you flip any of the, if you flip, a literal here, that literal bring the least amount of break values, so least amount of break on the other clauses. So you have thousands of clauses, and you choose one clause. Within that clause, you have 5 literals, let's say, and these 5 literals probably exist in many other clauses as well. And they might be the other clauses that those literals consist can be satisfied or unsatisfied. We don't know that. And when we try flipping the literal, so we flip the first one and check if all the other clauses that has this literal, did they change at all? So did we make a clause that were satisfied before unsatisfied?
Yeah.
And then we try all the other ones and then find the best one that breaks the least. That basically does the local search convergence. And then in a relatively easy problem, so medium-sized problems, this converges very fast, because as you flip the variables, at the end you end up with almost all satisfied clauses, maybe one that is maybe flipping back and forward. And with this random walk process, you will find the right assignment for that. But as it gets complex, this is a local search, and we will try to find it. So for actually, this WalkSAT algorithm is very good for medium hard, easy and medium hard problems, because it has a very good convergence rate and it's much faster. But if the problem is hard, where there are a lot of dependent clauses that impact each other, then it might find some time to converge.
I see. Thanks, Akif.
Okay. So what additional heuristics that we have? So we say for choosing the best, we choose the best break count. We use taboo search to avoid getting stuck in a particular region. So this flipping back and forward concept that I mentioned before. So taboo search is basically keeping a list of moves that we have executed. So list of variable flips that we have done. And we want to avoid that for a foreseeable future, for some time, so that we don't get back into the same state again. So this basically, this avoids going into a kind of a loop, or escaping a bit and then doing some other flips and coming to the same local minima with a different way. We want to avoid those situations. That's why we keep a taboo list. This taboo list is usually experimental. The length of this taboo list, so how long we will keep this forbidden moves, is experimental and highly depends on the structure of the problem. So yeah, this is usually, for other problems, we use square root of n as a length of taboo list. There is additional heuristic called, so meta-heuristic actually, it's called simulated annealing. And this helps us converge according to the time and make our convergence faster. And how it works is as follows. So if a particular flip that we are considering is improving the solution, we execute it. So in this random walk part, in here, so flip a random atom in C, in this part, if this improves, we execute it no matter what. But if it doesn't improve, we choose whether we are going to execute this variable flip with the probability of e to the delta over t. T here is the remaining time. So what happens is that as t goes lower, our delta will be negative because we are making the solution worse. As t goes lower, the probability that we will execute worsening moves is getting close to 0. But if t is higher, if we have a lot of time, then e to the power of 0 or something small will be close to 1, and we will, with a high probability, we will execute that move. So basically, this simulated annealing approach helps you keep the divergence and random walk stochastic nature of the algorithm in the beginning when you have a lot of time. But as you go to the end of your time limit, it forces you to converge more and more. Yeah, this algorithm is used in many other optimization problems as well. So if you can, actually, you don't even need a heuristic or anything to have to solve any optimization problem. So simulated annealing is a very generic framework that basically solves any optimization problem if you can represent a particular move. So here it's a flip, a variable flip. In some other case, it might be something else, but it's just to note here, it's a generic framework for solving optimization problems. So what's the quality of performance is that there are different types of set problem classes, and the performance differs a lot between WalkSat and also complete algorithms. Even for complete algorithms, different type of set problems result in very different runtimes and results, solutions. So we can't say anything, but we can make some very general comments, is that local search-based approaches performs poorly on very structured and hard problems where you have a lot of dependent clauses, and the global minima is, there's only one global minima that is very hard to find. Then it is very hard for a local search to find it. But if there are many global minima that you can't find any of them, so there are many satisfying assignments that satisfies this particular clause, WalkSat will probably converge faster than a complete algorithm. So most of the SAT competition winners are complete methods, proof-based, so CDCL, conflict-driven closed learning. The reason for that is, SAT competitions have very structured and hard problems, and proof-based solvers are learning the clause along the way and reducing the search space as they go. I mean, they take some time to find the solution, but at the end, they eliminate all the other possibilities by learning the clauses and then find the best possible solution. Yeah, we mentioned if there are many local minima, WalkSat converges fast to a solution. And also there is another type of, so another variation of SAT problems, it's called maximum and weighted SAT. And WalkSat is actually quite successful in those problems because we want to maximize the objective value, and local search is usually better in objective. I will be talking about max and weighted SAT for a little bit at the end. So in one of the papers, they made a comparison between WalkSat and DPLL, which is unit resolution DFS on this binary tree. The performance of DPLL, as you can see, is varying a lot depending on the problem and also close to symbol ratio. The reason for this is because learning and exploring this DFS tree might take very different times depending on which initial state, which initial literal you started with, and which initial assignment you started with. And also close to the literal ratio matters. But WalkSat is more or less related to the close to symbol ratio. So if you have less symbols and more clauses, WalkSat is very good, because if you flip a Boolean variable in a clause, it will likely not impact many other clauses, because each clause contains only a handful of literals. But if the number of literals per clause is very large, then flipping a clause, a literal in a clause, will likely impact other clauses, because most of the other clauses contain many literals that might be flipped someplace else. So this also kind of proves and concludes that if the number of symbols, so number of literals per clause is lower, WalkSat performs a bit better. So some problems are not satisfiable, or the user wants a reasonable answer within a given time. Even if it's not satisfiable, he wants to have maximum number of clauses that are satisfied. So MaxSAT tries to achieve the best assignment that results in the most number of clauses satisfied. And this is useful in some areas. I will show you an example later. So all clauses are equal, but some are more equal than others. Yeah, we can have soft clauses and hard clauses. So for hard clauses, we make sure that they are satisfied. So during this solver, they have to be satisfied. And for soft clauses, we care about the count of it. So number of soft clauses that are satisfied, we want to increase that. And for weighted SAT, it's the same story. It's just instead of discrete values for each clause, so satisfied or unsatisfied, so 1 or 0, we assign a weight, so importance to a particular clause. And if we assign higher weights to a clause, it means it is an important clause that needs to be satisfied. And our objective is basically to increase the total sum of the weights or the number of satisfied clauses. So we came back to this package upgradability example. Here we saw that this is not satisfiable, but how about what is the maximum amount of packages that we can contain in a system among these 4 packages? What is the assignment such that we can have a maximum of them in the system? And this is a problem for actually MaxSAT problem. And the MaxSAT will satisfy most of the clauses here. And you can give importance to the clauses, but I think for this case, if you model it with just MaxSAT, just giving 1 to each of them, it will give you that this P1, P2, and P3 can be in the system at the same time, and this is the most satisfying. So this is the assignment that satisfies most number of clauses in the Boolean equation. So actually, it has a tangible use case that we can see, and there are many more, but this is just an example. Yeah, that was it. Thank you very much for listening. If there's any questions, I can take them.
What should we understand from this last phase?
This is just a joke about logic. So nothing.
Thank you, Akif. That was a very good presentation. Anyone with question? Any question? No question? Okay, I had a question and I asked it, so I used my question.
Thank you for the presentation. It was clear for me, so I don't have any question.
Yes, we explained everything so clear, so we cannot ask a question.
Yeah.
Okay, that's I mean that's great. If you guys want to see, if you want some references to any of the items that I mentioned, or want to do further reading, you can just reach out to me and I will send you the links. Yeah.
Yeah, maybe if you have time, you can, if there are some public resources, you can share it maybe on Slack.
Yeah, sure.
Some important papers or links. It could be great, I think.
Sure.
And thank you again.